Okay, welcome back. The second talk of this morning will be by Kausik, and he will talk about functional bootstrap for local field theories in AdS2. Please, Kausik, take it over.
Okay, thank you, Francisco. And hello, everyone. Let me begin by thanking the organizer for giving me the chance to speak here. And I'll be talking about some ongoing work with Miguel Paulos and Zhechuan Zhang. Zhechuan is here. So this is something that we're kind of trying to do from a long time. And okay, the main result is that we quite don't know how to do it yet. But we have made some progress, we think. So I will talk about that direction. So I want you to keep in mind that there are essentially two models that I want to talk about today, and they are, like, from the Bootstrap perspective, the way I will formulate the problem, they are quite similar, although the approaches to attack them would be very different. So one of the model is so as you can see, there are some field theories in AdS2. So we have some action in the bulk. So one of the model is where you have the free theory in the bulk and you have some 5-4 interaction in the boundary. And the another model is basically same action, but now the 5-4 interaction is in the bulk itself. Okay? So these are the two models that I want to talk about. And in a sense, they are kind of similar, like the way I'm going to say it. But they are indeed very different model. And in fact, this model is, like there are people, Bernardo, there is Connor, Philin, Leonardo. All these people have worked with this model from a long time, and they have, in fact, right now, like in the last work of Connor, they actually they can show that this long-range easing model sits at the kink in d equal to 2 and 3. But still, I think there is something to learn in d equal to 1. To see this model here, what we need to observe is that if we integrate out this direction z, then actually this action, this particular action, they on the boundary, they look like exactly the non-local action. So, this particular model where the interaction is only at the boundary, that model becomes the very familiar non-local action for, say, long-range easing model. This operator becomes relevant for certain dimension of the delta phi, and then we can flow to the IR fixed point, which is in the same universality class as the long-range Ising model. So, in AdS, this Lagrangian, this field is in the bulk, and then this is the boundary operator.
Yes. I mean, boundary condition are you, which, I mean, there are at least two boundary conditions. Yeah.
You mean how the phi gets mapped to the boundary phi?
Are you in mind the usual Dirichlet boundary condition? You are only discussing one condition?
Yes, so depending on the range of mass, actually depending on what delta phi want, we have to choose the one branch or the other.
Yes.
So
You always choose the what is called the regular one.
yes.
Okay, thanks.
Okay, so here the problem, okay, one of the things that would be nice,
Sorry, but if you want to go all the way to zero dimension, you have to choose the delta minus.
I
If
have
you
to
want-
choose the delta minus, yes.
So you're not always choosing the regular one. Sometimes you also have the irregular one.
So, I'm not always choosing the which
So
one?
if you wish to reach the unitarity bound, which I'm sorry, maybe I'm getting confused because this is a one-dimensional theory, which I'm just a little confused. Do you really always choose a regular boundary condition, or sometimes you need to choose the irregular one?
So by regular you mean do I
Delta
need to...
plus versus delta minus.
Yes, I need to choose delta minus to go towards 0, yes.
Okay,
This is what...
thanks.
Okay. So here in higher dimension in d equal to 2 and 3, like, so let me just draw in delta phi. So delta phi, there is a range. So that starts from 0 and ends at 1 by 4. So in this range, there is always a fixed point of this long-range Ising model. And here, on this side, it can be described as this free field theory in the bulk plus some boundary interaction. But on the other hand, here, there is no known duality like d equal to 2 or d equal to 3. Like in d equal to 2 and 3, we know that we can couple the short-range Ising model to some generalized field, and that gives a perturbative description here. But this picture is missing in d equal to 1. So it would be nice to get some understanding about this problem. Anyway, so what we would try to do in Bootstrap, this is delta phi, and I'm just talking in terms of delta phi actually. That on one side you have access to like perturbation theory because it's like a generalized free field coupled to some boundary interaction. But on the other side you don't have such description. Okay, so that's sort of the brief motivation to look for this kind of model. But now I will go to the Bootstrap setup. So we will use functional Bootstrap. So I will briefly introduce functional Bootstrap. So just as usual, and in this talk actually I will only talk about correlator of one operator, that is the fundamental field phi in the boundary. And of course this is the known thing. So this correlator, and then Dalimil and later on Dalimil and Miguel, they proved that this correlator admits a different type of expansion, which is different from the usual block expansion. And this correlator can be expanded in terms of blocks, which are called Polyakov block. This Polyakov block, they are crossing symmetric on their own. So therefore you don't gain any extra constant by demanding the crossing symmetry. On the other hand, if you write down the conformal block expansion of the Polyakov block, you will see And delta n here is 2 delta phi plus 2n. So when you expand the Polyakov blocks in conformal blocks, you see there is this physical block, but then there are these unphysical blocks. And the statement of this functional bootstrap is that if this gives rise to the same correlator, then this coefficient, when summed over the spectrum, they should vanish. So this results into the following two discrete set of equations. Where n is non-negative integer, and the crucial claim that Miguel and Dalimil they proved in their paper is that this is equivalent to the following crossing equation, right? And it can be seen very easily by the fact that Polyakov blocks is crossing symmetric on its own. So if you just impose the crossing symmetry, it leads to the equation that this is equal to this. And there are some subtlety here. And the subtlety is that while doing this, you are actually exchanging.
Perhaps you should remind people that F is a combination of the usual blocks.
F delta Z is the combination of the usual S channel and T channel block, yes.
Yes.
Oh, sorry. Okay. Okay, so these constraints are equivalent to the crossing constraint, and we will be looking at these equations, but the subtlety was we are swapping the sum over n and sum over delta, and this is only possible because since these are infinite sums, so we have to examine carefully the tail of this sum, the large delta tail and the large n tails. And this is what they show in the paper, that if they have certain bounds, then this swapping is always allowed. And that bound, in terms of correlator, it translates to the Rayleigh boundedness of the correlator, so which basically means that when you are taking Z large, this correlator cannot grow faster than a constant. If the correlator falls into this category, then the OPEs will be bounded in a way so that we are allowed to do this kind of swapping. Okay? So that's the claim of functional bootstrap. Now instead of using the derivatives, we use these functionals for numerics. So I will tell just I'll just say one more connection of this Polyakov block with something that everyone is familiar with. That is, these Polyakov blocks are actually they are the sum of Witten diagram in S channel, and then the cross channels, and then you have the contact diagram, something like this. So this is just an identity, there is no holography or anything, but this is the identity that Polyakov blocks can be written down in terms of the Witten diagram and a contact diagram with some specific coefficient. This point of view is very important for doing an actual numerics because we can construct this functional explicitly from this Witten diagram, and thanks to Zinan, who wrote down some, based on some old work of Leonardo and collaborators, that this Witten diagram satisfies certain identities, so that actually you can find this functionals recursively, knowing just two seed block. So you just compute two-seed block, and then everything, for all n, you can construct them recursively. So that's very powerful tool for actual numerical implementation of this block. And then the last point about Polyakov blocks is, or rather the functionals, this alpha and beta functional, is the, which is important, is the duality relation. So the duality relations are the following orthogonality conditions. So let me just draw a picture which will make it clear that what this orthogonality means. So suppose I am drawing alpha 0 delta. So if this is the alpha 0 delta functional, then the orthogonality tells that when it acts on the crossing vector, which is delta 0, so when delta equal to delta 0, that is n equal to m, so at that point this is 1, so that's what it's saying, and then in rest of the pieces, this is 0. Okay, this has double zeros, except the point here, which is coming from this derivative relation, right? So this derivative is actually with respect to delta. So one should understand this, that the derivative is acting on the function of delta, and then you are setting delta to delta m. And the beta n functionals would be similar, except that they will have a first order 0. So when n equal to m, there will be a first order 0. But there will always be a first order 0 when m equal to 0. So there are always some functional which looks like this. Most of the places they have double zeros, and then some places they are either 1 or 0, first order 0. This is what this, the functional has this property. Now you can ask, like, what are they good for, like whether this property itself has any immediate consequence. And like just looking at this functional, you can see that this will give an instant bound, because suppose I say that my first operator that appears at 2 delta phi, then I can ask, like, what is the maximum OP that this operator can have. Then this functional is an exact, gives an exact bound for that. So I can write that a 2 delta phi has to be bounded by the action of this functional on the identity, right? Because there's nothing else, so only these two terms contributes. So this positive should be bounded by this one, and this is 1, the functional is 1 here. So the OPE is bounded by this quantity. So we get an immediate bound. And so that's why these functionals are interesting, because they have very nice properties, so that instead of using like lots of derivatives like this, using few functionals, you can get like very good results. So they are very useful. And then there are two more properties that I would like to point out. One is looking at the large delta limit of these functionals. So at the large delta limit, this functional goes as the, this is the 1 by a delta GFF, meaning the OPE of GFF. So it has growth like the OPE of GFF. GFF is a generalized free field theory, times a power law, which goes like 1 by delta Q. So what does it mean? It means that if I multiply, say, some OPE times beta n delta, then actually this this quantity can go at most like a power law, which is very different from derivatives, for example, where you will see exponential separation. And this property of functionals, actually, this is the property why these functionals are so efficient, because they care for their tail. So you can get better bounds. So this is one of the things that I would like to point out. And then another property is the large n limit of these functionals. So for example, if I take the beta and delta, then in the large n limit, there is a special piece which goes like 1 by n square, and there the coefficient is actually another type of functional which falls under different class, and I will discuss that later, like what that functional is. But that property I'm going to use in my next discussion. Okay, so with that, let me go to the next discussion. So the point is, we want to bootstrap just 4-point function of 5, 5, 5, 5, right? Now suppose you do a gap maximization. What is the answer that you get? What is the spectrum that you see in your extremal solution? The spectrum that you see in the extremal solution is basically, there is a identity, of course, because you always include that, but then there are operator which can be roughly thought of as the deformation of GGFF. So you have some operator which can be thought of as, like they have some anomalous dimension, but you find always spectrum like this. You don't see any other operator. There is no operator which you can think of, say, something like phi square n in terms of free theory limit, like something like a multi-particle states, or maybe even higher particle state. All these are absent. So all you see is the double field operators, these double field-like operators. And that's a very interesting observation, because now you can ask, like, what is the property that is special to this LRI up to this contribution that I can use so that maybe I can catch the flow of LRI. So to do that, we will talk about, we will see perturbatively what it's trying to tell us. So in one end, as I told you, like when delta phi is 1/4, at this end the theory is a generalized free field theory plus its perturbation. So at this end, if I do the perturbation, then up to epsilon cubed, where all the double trace operators appear, you will see that all the data that appears here all these data for, and here the only thing is the delta 0 is not here. So except that, so all delta n greater than 0, so these are the spectrum of GFF, right? There is operator which is 2 delta phi plus 2n. So for all n except delta 0, you have some expansion of this type, and similarly for OPE. And that can be fixed by dimension of single operator, which is the delta 0. If you know this, then you can uniquely, perturbatively force it to be LRI. So you can think of this when you do Wilson-Fisher perturbation theory, actually up to epsilon cube, it's unique. The solution is unique. But the uniqueness comes from the fact that you have a conserved stress tensor, which is not true for LRI. You don't have a conserved stress tensor. So can you find out some principle which will allow me to fix the value of delta 0, and then I can find a unique solution to this set of equation. Yes, please.
Is the boundary or bulk coupling? Right?
Yeah, I'm right now talking about the one where it's in boundary, so which is related to LRI.
So, yeah, just maybe I missed the stupid point. So if you set lambda equal to 0, you have a GFFF for any delta. Now, right? It's a GFF, it's a continuous. Now, why you have a GFFF now only? I mean, maybe it's obvious that lambda
no,
can be tuned
because,
such that...
because if I want to identify that with the LRI flow, then the delta phi should have this dimension. That's why I'm fixing it to be this. Otherwise, I can't flow to the LRI point. So LRI exists only for this region, because only for this region phi 4 is relevant.
Yes, but then you assume that you reach indeed a fixed point, which is maybe it's obvious, but... So you say that at delta equal to 1/4, lambda phi to the 4 is marginal.
Yes.
Right, okay, but then are you assuming that you flow?
Well, I'm doing Bootstrap, so I'm assuming that I'm at the CFT, like at the fixed point.
Okay, you assume you...
Yeah.
Okay,
I'm at the fixed
fine.
point.
Okay.
But the point is there are many solutions from just this bootstrapping single correlator point of view.
But you could flow also with the relevant operator, not necessarily marginal, not classically
sorry,
marginal.
there are?
I mean, in principle, you might choose also other value, which has, of course, relevant, so less than 1/4, and they will also work. If you land on a CFT, then you bootstrap and you see whether the assumption is correct. I didn't get why you take delta phi equal 1/4, it's a special value, aside from the fact that this is the value for which your perturbation is marginal.
So LRI exists for all delta phi, where I can parameterize this with epsilon, and this epsilon can go up to 1, which is basically 0. But I'm doing a perturbation for a small epsilon when it's marginally relevant.
Okay.
Phi 4.
Okay, you have in mind some future epsilon expansion of
yes,
some kind.
Yes.
Okay,
I'm
good,
doing
thanks.
the perturbation
Okay,
in epsilon.
Thank you.
And sorry, just notation, in the equation with gamma, on the left-hand side, there's gamma n, I guess, not delta n. You're only writing the anomalous dimension there, right? It's not that there's some operator with dimension 0. Okay, there's 2 delta phi plus 1. Yeah, okay, sorry, thank you.
No, sorry, this is my mistake. Okay. So what we observe is that, so we are looking for one extra equation which will fix the dimension of delta 0. And what we observe is the following identity, that suppose you are in the bulk and you are looking at this contact diagram, then for this value of delta phi equal to 1/4, which will give you the subleading correction to the anomalous dimension. So you will see that this diagram is actually, if you integrate out the z direction, which is the bulk direction, then this is exactly the flat space phi 4 diagram times some coefficient here. And so what I'm trying to say is that this flat space diagram has only coefficient, which is there is only single block in this diagram. So which basically means that only it gives anomalous dimension to just delta 0 and no other n. So generically, this type of diagram will give you it will basically source anomalous dimension to all operators, and the gamma n will go like 1/n² in that case. But for this case, it's actually 0, and only the n equal to 0 terms survive. So only delta 0 gets anomalous dimension. So this gives us a hint that it could be that this solution is actually has this extra suppression. Okay? I mean, usually the gamma n should go like 1/n², but this is absent in the leading order. Now, we assume that it could be the case also in the subleading and so on. So this 1/n² term is absent. Now, if you remember, I point out a property that beta and delta in the large n limit has this behavior, that it's related to some other functional, which comes with 1/n² behavior. So actually, if you do perturbatively the computation, you will see that this part, this 1/n², actually comes from this piece. So what we do is that we say that let us impose that this guy is 0. Now, this may not be true, because this is very, very strong assumption, okay? It's strong because this means that I am assuming that the correlators are actually very super bounded, which basically means that when z goes to I infinity, the correlator is has this kind of subtraction. It's not order 1, which is the usual case, like in usual theories. Now, this assumption may be wrong. So we just wanted to, but on the other hand, we just wanted to see like what happens if we just impose this. It turns out that since I now have one extra equation, you remember that in alpha n and beta n set, there was no beta 0. So that was the missing piece. That's why I have this ambiguity. Now that I have an extra equation, so all my solution is fixed. And it turns out that this indeed, up to epsilon cube, fixes the solution. Okay? Now, at epsilon 4, immediately we are in trouble because there will be multi-twist operator, and these functionals at 1, they blow up. So when phi 4 will appear, it will blow up. So it will have a suppression in epsilon. But on the other hand, if you take the tail, if you take the tail of the phi 4 tower, so phi 4 will come with its own tower, right? It will have dimension like 4 delta phi plus 2n plus other things. So this multi-twist tower also diverges. So they can cancel, but we don't understand how exactly they will cancel. But on the other hand, it's okay, but at least the double trace operator, which uniquely fixes the data up to epsilon cube, we just go ahead with this and run the numerics just to see if we can get some curve which kind of has the right property, like which is expected for LRI. But this could not be LRI, okay? This may not be LRI. I mean, we're not claiming that this is LRI. It's just that we have this perturbative evidence, and then we want to just see that how this functional space behave like. Like, can I get some sensible plot out of this? So that's the thing that we do for this model. And just as a check that this is not an accident, what we do is that we also compute the same model, but now it's a free theory in the bulk, but in the boundary, instead of phi 4, we have a phi cube theory. So something like a long-range Lee-Yang. In that case also, we saw that this equation fixes up to one loop, all the data. Remember that in the two loop, there will be other multi-twist operators. So
sorry, can you say again this logic? So of course, we know that there are these ambiguities that only get worse and worse as we go on in the epsilon expansion. So imposing this condition is just for convenience, or?
We just wanted to fix the whole double trace tower up to epsilon cubed, and if I impose this condition, it reproduces that answer. That's all I'm saying.
Sure.
Yeah.
You could also just parameterize your ignorance and go on, but that the more...
You are saying like why I'm not going to epsilon 4 and...
No, I mean, the fact that the correlator should be bounded, it just follows from sacred principle. Super bounded, we don't know, and that introduces the usual ambiguity. And then this ambiguity only gets worse at higher orders in epsilon.
Yes.
That's my understanding.
Yes.
So if you just want to do a systematic epsilon expansion, you just parameterize your ambiguity. There's nothing you can do about it. And then, I don't know, clearly by definition, the long-range Ising model has to be somewhere in this space of perturbative series that you have, because there are free parameters that a priori it cannot be fixed.
Yes.
But you're not doing that.
No.
So what are you doing again? You're fixing the ambiguity by imposing this condition.
Yes.
And then how do you run the numerics?
Yeah, so in the numerics, we are not, now we are thinking that we are just doing a numerics for this extra, basically for Rege superbounded case.
So you are doing the numerics imposing this condition?
Yes.
Okay.
Yeah. But there is no argument that this should be correct, like this should be LRI. The evidence is only perturbative. Yeah.
In particular, whatever solution you get will never have multi-trace towers. That is guaranteed.
In numerics, yes. In numerics, yes.
In numerics, yes. And
In perturbation theory, it's also true because this existence of the tower, you impose it, right? Like, you can solve without them.
But then I guess the expectation is that in long range using this tower is there.
Of course,
yeah,
of course,
okay.
of course. So it's like what the best you can do with just single correlator. That's what you're asking, basically. So I'll just say the last thing about the numerics is that so usually, so as I said, like, so the dimension is from 0 to 1 by 4. It's here. And then if I don't include this extra sum rule, then it goes like this. So this line is 2 delta phi plus 1. This is 2 delta phi. This is delta phi axis, and this is the gap. That is the first operator that appears in phi phi I plus O delta gap. Okay, so this gap, if I just do numerics just with the usual functional, I will get this line. Now, after introducing this extra functional, which is this beta tilde 0 delta, we again do the numerics. And if I don't assume anything, then it doesn't improve much. It gets down to somewhere 1. And then actually we assume something extra. What we do is that there is some, we say that there is no operator between 1 and epsilon. Like this I want to change. This epsilon is different. Let's call it epsilon 1. This is not the same epsilon. So I want to just vary this. And I want to see, and then do the maximization and see where it appears. So there is a critical value after which no operator appears, like there is no solution. But for the last point, if I plot it, it gives me a curve which interpolates from like half to 1, which is kind of expected for this type of model. But again, this is not LRI. But indeed, if you plot the epsilon expansion result, they match up to the limit where it should, like, because it reproduces the correct epsilon expansion. So if you do numerics with this, of course, with certain optimization, this will match. So this is the story about LRI. Which I should not call LRI actually, but this is the exercise that we do. And right now what I'm doing is that now that we have a different method due to Connor and collaborators, I'm trying to do the same thing for 1D, and I want to check it against this. Of course, this will not be exactly same because it's a multi-correlator setup, so the bounds will not be exactly this, but it should have whether the similar pattern or not. That's what I want to check. But
like it's not a systematic formulation that allows you to go to higher orders, but there's this old paper by Kosterlitz perturbing around the crossover end.
So it just gives that 1 minus delta phi to the power half, I think.
Something like that.
If you're asking whether that exponent match, no.
Okay.
In this end, it doesn't match. I am not allowing for certain region, like no operators, and then doing the maximization. Okay, so this is what we are doing now. We are just repeating their computation to check that if it works, and then try to make sense. What does it trying to tell us? Okay, so I'll go to the next part. But in general, we are interested in a setup where we can kind of impose this constraint more naturally. Like whenever I have a local field theory, I should be able to like impose this constraint more systematically. This is some stuff that we are trying to work out. So, okay, so to impose locality more systematically, Nat and Miguel recently introduced some extra conditions, and I will describe a bit about that. And then the goal would be basically take the crossing equation and take these extra locality conditions and bootstrap with that bigger system. Okay. And also I must mention that kind of the similar ideas, Balt and collaborators, they also have done some work on this line. But these functionals I will describe, that was done in Nat and Miguel's paper. And then very recently, right after that, Marco and Joao and Taro, they also has a paper which is very important to make it work for things that we will do. So here, so we want to impose locality. By that, we mean that suppose I know that it has a, suppose I know that there is a local operator in the bulk, and I want to impose this constraint on my, I somehow want this boundary and bulk to talk to each other. Basically, I want to tell them that there is a local operator in the bulk so that I can disallow all the unphysical solutions and I only bootstrap the local theories. That's the idea. So here the construction goes as follows, that imagine that there is a local field. So then this field, so this is my boundary and this is the bulk. So this field will create a state on these hypersurfaces, and then you can basically do a time, you can evolve it back in time, so which means that you are creating this smaller and smaller sphere. And eventually it will project into a boundary insertion here, right? So what I'm trying to say here is that a field in the bulk can be expanded in a basis in terms of the boundary operator. So there is a expansion of this type, and we want to make use of this to impose this locality constraint. So for that, we want to take this form factor So we have two boundary operator of some, okay, let me just call it maybe phi tilde. So these are boundary operators, and this phi is a bulk operator. So this is the object that we want to study. And this, this depends on a single cross ratio, Z, which is defined in terms of this coordinate. The expression is not important for this talk, but the point is that they can be expressed in terms of the single cross ratio, and then this Fz can be expanded. So basically what you do, you just expand this operator in terms of the boundary operator, and then this will give rise to the boundary OP. You will have a boundary OP coefficient, and then you will have a 3-point function, which is because you have three boundary operator, and then there will be a block. So, okay, so this can be written down like this, and there are some nice properties that this function satisfy, and one of the property is in Z coordinate. So if you are in this region, minus infinity to 0, here you can have a, you will have a cut of this function, but if you are here, let's say 1 to infinity, then there is no cut. of this function. But on the other hand, this block has a cut here. So you can already see that you have to tune your coefficients in a very special way so that after doing this sum, this cut should vanish, right? Because this is unphysical, because this guy doesn't have it, right? So the condition is that there is some discontinuity of this function, like BOE basically breaks down there, and that should be 0 after resumming over this thing. So how do I construct some functional to this? So the idea is I just integrate my functional, I just integrate my this function with some kernel. Let me call it kz. I integrate this over some contour, which is this contour, but this function is completely analytic, and I choose certain kz so that it tells me that at z goes to infinity, I can forget about the arc. So then this quantity has to be 0 because it's completely analytic function. And then I can replace with this expansion, and then I can basically close this towards the cut, so which will gives rise to some formula that would look like mu delta lambda phi delta times some functional. It's just integration of this with the discontinuity of this block. So, and as you see, like I have again put an index n here. That's because you can construct not just one such functional, but basically a class of functional. And that basis is a complete basis in the sense like the fact that this guy has to be 0, this condition is completely encoded within this sum rules. So these are my locality sum rules. And one more thing which is important is that there is some parameter, let's say alpha. That's because this kernel has certain fall-off and they are parameterized by some alpha. So this is not fixed because unlike my correlator, we don't have an idea like how this should be bounded at infinity. So you just allow for this extra parameter, which you can tune to drop the arc. Okay. So that's the basic idea, and if you are curious that whether these type of functionals you can also get from Witten diagram, the answer is yes. If you consider some Witten diagram, and if you take this phi tilde with some, say, psi delta bulk field, sorry, if you have an exchange, and if you compute this Witten diagram, you can read off the coefficient in the conformal block decomposition, just like what we do for alpha n and beta n. You get exactly these functionals out of those expressions. So kinematically, they are related to this Witten diagram. So, okay, anyway, we have this functional, and this functional also satisfy a duality condition, and the duality condition is that is the following. So these are single zero functional, that's why they have no constraint on the derivative, but they are just 1 when n equal to m, otherwise it's 0. This delta m is the same, it's the 2 delta phi plus 2m. These are the location of the double twist operators. Okay, so we have locality conditions, and now you see, okay, one more thing that I must mention, that you can't find such type of functional for n equal to 0. So this is missing. It's like a subtraction in this alpha and beta n story. So this theta n only is from n greater equal to 1. Like this exists only in n greater equal to 1. There is no functional called theta 0. Okay, so that's what this locality condition tells us. Now, of course, we want to do numerics, so there is a crucial equation which is missing from this. So we have an expression which is something like square of the OP, and then we have some expression which is like the product of the mu and the OPE, but then we don't have an equation which is square of this, and which you can guess that it should come from considering a 2-point function in the bulk. Now this also depends on a cross ratio, but what equation you derive out of this, because this, like we don't know, like for general operator, how do you derive any equation that will constrain some data? Now this is where Marco, Joao, and Taro, their work comes in, and I will just write down the formula. I'll not review it because it's also a big thing. I can't cover this within the time, but essentially the point is that they have an equation, and that equation is very nice because suppose I want to bootstrap some action in the bulk which has like exactly what I was writing down before, that it has this form. So it is free theory in the UV, and then it has a coupling phi4, okay? So one of the sum rule that Marco and collaborator gave us is the following, that looks like this. Like it's some functional, that's a different functional, and it is related to the central charge of this UV theory. So in this case, it's a free theory, so it's related to this, this quantity. So under this flow, like in the bulk you have a flow, so your OPE data under this phi4 flow is constrained by the central charge of your UV theory, which is in this case free theory. So this is one equation, and this is enough actually that we can bootstrap now. But they also gave another equation, which is like this. So they also consider some form factor, and they can derive this. Now the reason they can derive all this because they consider a very special function, which is the stress tensor. Or for our purpose, what is important is that we want to consider the trace of this stress tensor in the bulk. And by using word identity, one can derive this, and then looking at the some short distance limit, one can derive this functional. That's why it's related to CT, because you have to look at these short distance limit. But now I have a complete setup, and I can do a bootstrap by mixing this boundary correlator and the this bulk trace of stress tensor. So I will the last part that I will describe is something about that. One thing that I want to point out in this setup is that, remember, our functionals are alpha and beta n, these functionals. So let's say this sits here. And then you have this equation, which is this theta 0 tilde delta. And then you have an equation, which is this theta n delta comma alpha, which I was describing before. And then also I have kappa delta alpha. So this sits in this corner. Now, before you do the bootstrap, you first need to compare the scaling, because they scale very differently. So you should make sure that you can actually impose the semi-definiteness condition. Otherwise, it will not, it's not a rigorous bound. So what you will realize that after doing some rescaling of the OP, these guys, I already told that these guys grow like 1 by delta cube up to this growth of delta GFF. But I rescale that, and then it goes like this. And then it goes like that. And this guys has certain follow-up. I don't want to write them, but I just want to point out that there is some number, and then there is some alpha. So, and you have to make sure that you choose the right alpha such that these guys form a positive semi-definiteness. These guys have a chance to form a positive semi-definiteness definite matrix. And yeah, because even if these sum rules actually they converge, like for certain alpha, this may not work. So you have to choose certain alpha to make this work. And as you can see, like it would be a bit it's not clear how would you do this if you use to bootstrap this 4-point function derivative functionals, because they will be exponentially suppressed. So it will be very hard to impose this positive semi-definiteness. So it seems like you have to work with these functionals. And then, okay, so about the results, so we tried this bootstrapping this, and the first thing that we noticed is that we tried to minimize the CT, and in fact, this solution turns out to be very simple. It's basically saturated by a generalized free fermion, and the CT minimum is half. So, which is something that we expect because this is the UVCT, so it's like the flat space central charge, and this is the minimal value. So this we can get out of this. So this is a nice consistency check. And then the problem that we were looking for is the following. Suppose you just take the 4-point functions of the 4 field, so you don't take anything about these locality conditions, and you do this problem. So you say that you have some operator at a particular dimension and you want to maximize the OP. So this is the problem that Miguel and Bernardo, they looked at before. And if you plot the diagram, you will see that you are going to get some diagram like this. And here you can show that, actually the epsilon expansion result, they match pretty well, like as you keep adding more and more term, and up to epsilon cube actually they match. And then of course you expect that epsilon 4 will not work because, as I said, that these extremal CFTs only have double trace-like operators, so there are no particle production, no multi-trace operator, so this bound will not agree with what you expect from the bulk phi-4 theory. So to improve that, maybe you can think that I can use this extra sum rules which comes from the locality, and I can improve the bound. So first of all, the thing is that we can never get phi-4 with a finite number of correlator, because in 1D this works with finite set of operators. So if you include one more, it will have 2 tower of operator, so which is not phi-4, because I would expect that a generic phi-4 will have all the multi-traces. But then the point is, can I correct it loop by loop? Like, can I make it correct to 4 loop instead of 3 loop? So that's basically the goal. So in that, to try that, we did this bigger system. We included this locality constraint, and then we tried to solve it. So first of all, the thing we did is the following check, so as you vary this delta gap, which is basically this, and you maximize the OP, if you just take this extremal solution and now compute the CT, because you can solve for all the locality conditions with this spectrum, and you can solve for all the mu's, and then you can also solve for the CT. So if the central charge you get goes from 1, and it's here half, because this is generalized free fermion, this is generalized free boson, and there is a flow, and this curve goes from 1 to half. Okay, so notice that this is CT which is less than 1. So the central charge is less than 1. And now this is a problem, because in our setup where we want to bootstrap this free theory plus phi-4 interaction, we have an equation which is this sum rule, and this sum rule is equal to CT, which we put to be 1, right? In some normalization, the free theory, free bosonic theory has the central charge 1, so we want this sum rule to be satisfied. So I always want this to be 1, right? Because I want to bootstrap this theory. But on the other hand, there exists this extremal solution where it is less than 1, so it solves all the alpha n and beta n equation, but the central charge is less than 1 here. So what this equation will do is basically it will add some junk, which basically means that it's a fake operator here, and then it will turn the OPE of this guy to 0. So if it is less than 1, then it's bad, because then we can't improve the bound, because we can see that there is this way that we can always solve the equation. So the bound will only improve if somehow the extremal solution that we get out of the runs without imposing the locality conditions, if we see those with that set of extremal solution, CT is bigger than 1. Only then the bound will improve. And indeed, when for this same plot, so what we do is that we fix a ratio of the lambda delta gap and mu delta gap, and then we scan over it, and you are going to get a plot like this. And this particular, so this is for a particular value of delta gap. So you can do it for any delta gap that you choose, and for all of them you are going to get a plot which, all of them have this feature, but yeah, their values of course depends on what gap you are sitting in. But this line is basically the fact that you have this junk solution. So it gives you back the same solution, it just don't use the other equation because there is this ambiguity. But then when you go here, actually here it improves, and it improves exactly as expected. If you count all the degrees of freedom, then you have all the equation for solving this lambda, mu, and everything. But then you have one extra equation, which is this kappa equation that I was writing. And that means it can include 1 degree of freedom. So which you can think of like a representative of this 5-4 tower. So it has like one extra solution. So the solution looks, so here the solutions look like, so up to a point, the family of solution is a generalized free boson plus one extra operator, which we may want to call 5-4, but not quite. I mean, this is some operator that appears. And then rest of the places here, it's a GFF. It changes the solution, the nature of the solution, plus one extra state. And here it's GFF. At the minimum value, it's a GFF. And you can repeat this plot for all this gap, and you are going to get this plot. Now, this is, of course, we expected because, as we said, that we have kept this CT fixed, and there exists this solution, so therefore it can't be, it can't improve. So there is no natural way that I can say what would be my 5-4 theory from this plot. So that's a bit hopeless. So, but then the point is, this stress tensor wants to talk to all the operators. But since this guy's like phi will never allow to talk to like these extra towers, so this guy is roughly reconstructing the phi square operator, but it can't reconstruct the 5-4 type operator. It just have that extra one state. So, so to improve this bound and hope that this type of, like we can get match up to say G4, like 4 loop order, we at least have to include phi square as a external operator, which basically means that this guy as an external operator, and then run with this extra sum rules, and it will have a chance to reconstruct this exact, this and this tower, and it might work. But at the moment, because of this reason, this bound doesn't improve. So yeah, that's the story. And this is what we're doing now, including this phi square operator and locality operators, and see if it improves. Yeah, that's it.
Thanks. So are there any questions? I'd like to ask? Yeah, Marco. Just wait a second.
You said, I'm not sure I understood at the end. You said you're adding phi square as the 2-point function of phi square as an external operator now?
Yeah, this bigger system we want to consider. I mean, like in the boundary, I want to consider phi square correlator, so that now the 5-4 will be forced to appear. So there will be 2 towers, which is phi square tower and 5-4 tower.
And in the bulk?
In the bulk, still just this trace of
still
stress
just
tensor.
that.
Yes.
Okay. Thank you.
To get these plots, how many functionals do you use?
You mean this plot?
Yep.
Oh, this you can get like, some 5, 6 functionals.
Okay. What else? Okay, sorry. Yeah.
There's some lower bound on the alpha you can use depending on the bulk OP.
Where is the lower bound?
The values of alpha which are allowed for the local blocks OP to converge. I think there's a bound that depends on what appears in the OP of theta with itself. Is this ever, so there's some alpha min. Is this ever relevant? For instance, in the, you were saying you need to tune alpha so that all the matrix elements have the same behavior?
Yeah, the alpha is still bigger than that, yes.
It's always
yes,
that way,
yeah.
okay. Thank you.
Okay, if there are no more questions, let's thank Kausik again.